Hello, class. We'll do a play. Hazel. We'll do a play. Say butter. Oh, you'll do a sharky. You'll do a sharky. Okay. Do a sharky. Do a sharky. Oh, you'll do a sharky. Drop. You ready? Okay, do. Good baby. Good baby. You ready? Do. Good girl. Want one more? Do. Okay, we do one more. Say butter. 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 Good girl. Okay, that's all. That's all. Bye-bye. Bye-bye. All right. Do we have 20 people? We have 20 people. So I'm going to get started. Oh, I got to zoom in. And I need to autofocus. So this is AP Physics 1, January 15th, period 4. Doesn't want to focus. There it goes. So after today's lesson, there will be 2 weeks left in the semester, and I'm not going to do any new content in that time. So I'm just going to be reviewing for the final, and there won't be any assignments. So today's quiz is the last quiz, and then the final exam, and that's it. So I wanted to give people a chance to get caught up if they, because some of you are a bit behind on the homework, so I want to give you a chance to boost your grade. As I said at the beginning of the year, my goal is not to. I don't really want to give anyone a bad grade. I'm going to give you the grade that you earn, but I want to give you the chance to earn the best grade that you can. Okay. So you'll have 2 weeks to kind of get caught up, and during those 2 weeks, I'll be using my lesson time to do a quick review and then run it more like office hours. Okay. So we're going to kind of learn 3 things today along the lines of rolling motion. So let me just talk about last time. Last time we were talking about when something is rolling. You have V equals omega R. So this is when you are rolling. So the rate of rotation of something, which is omega, is connected to how fast you're moving. Okay, That's only when rolling. If you're in outer space, how fast you're going through outer space has nothing to do with how fast something is tumbling, right? But if you're on the ground and you're rolling, the ground is sort of enforcing this relationship between the two. We talked about rotational kinetic energy. And so we found that the total kinetic energy is equal to 1/2 mv squared plus 1/2 I omega squared. So we have a rotational kinetic energy. And we have a translational kinetic energy. Now, if you are rolling this, and this is a big if rolling, this expression simplifies into the following form: 1/2 mv squared times the quantity 1 plus I over mr squared. Okay, so during office hours, I think on Tuesday, I had a couple of questions about one of the quizzes where the object was not rolling. They were trying to use this equation, but the object was not rolling. Okay, so if it's not rolling, you have to use the top equation. Okay, so then we applied this to conservation of energy problems. All right. So let's do another example of a conservation of energy problem. So today is mostly just going to be examples. So let's say we have a hill, and the hill has an angle of 40 degrees, and it has a height of, let's say, 22 meters. All right, and we have a hoop. So this is a hoop. All right, and hoops have an inertia that is just simply mr squared. Okay, and so the hoop starts at rest, and it rolls down this hill. Okay, and so first of all, let's figure out its velocity at the bottom of the hill. So how fast is it going once it gets to the bottom of the hill? Okay, and then we're going to extend the problem. So the hoop starts at rest. It is not necessarily true that the hoop could start at rest. In fact, one of the quiz problems had an object that is rolling at the top of the hill. It's already rolling. So, so the energy at the top is equal to the energy at the bottom. Okay. At the top, we have potential energy. And at the bottom, we have rolling kinetic energy. Okay. Now, if this hoop had been moving at the top of the hill, we would have an extra term on the left-hand side for the kinetic energy of rolling at the top. Okay, so that the conservation of energy equation for one of those my phone is getting blown up here. So anyways, one of the quiz questions has the object rolling at the top of the hill already, so it has a kinetic energy at the top in addition to its potential energy. But this one, it starts at rest, so it has no kinetic energy at the top. Okay. So potential energy is mgy. All right. And then
What you do, Hazel?
Hazel's a funny girl. And then rolling kinetic energy is 1/2 mv squared times the quantity 1 plus I over mr squared. Okay. So we can see that this mass will cancel out with that mass. So these two masses cancel. All right. And you might be panicking because you might say, well, gee, Mr. P, you didn't give me the mass and the radius of this hoop. And it turns out that it's not going to matter, because if we take the equation I equals mr squared, which is true for a hoop, and we divide both sides by mr squared, we get that I over mr squared is just 1. Okay? So this I over mr squared, I can replace it with 1. And then I have 1 plus 1, which is 2. And then that 2 is going to cancel with the 1/2 here. So I have g times y equals 1/2 times v squared times 1 plus 1. And this will cancel with that. And so I have gy equals v squared. Gravity is 10. The height of the hill is 22. And so I can get the speed at the bottom of the hill. So that's going to be the square root of 220, which is 14.8 meters per second. Okay. But what if I wanted to know what is the acceleration? Okay. So what is the acceleration as it goes down the hill? Okay. Now, obviously, once it gets to level ground, the hoop is just going to keep rolling at whatever speed it had. Okay. And so what we're going to do is, if I ask you what is the acceleration of a rolling object, you're going to use energy to get the speed. And then once you have the speed, you're going to use kinematics. Okay, so we're going to go all the way back to kinematics. All right, and in particular, there's a nice kinematic equation, which was v final squared equals v initial squared plus 2 times the acceleration times the displacement. Okay, we know that v final is 14.8 because that's at the bottom of the hill. So we have 14.8 squared. We know that v initial is 0 because it starts at rest. So plus 2 times the acceleration, which we're trying to solve for. And now we have to be really careful because delta x is how far the hoop rolled. So you might be tempted to put in 22. But the delta x is not actually 22 because it's moving along the hypotenuse of the triangle. That's how far it rolled when it was rolling down the hill. Okay? So you got to... so this is the hypotenuse of the triangle. Okay, so I know that I have a triangle right here, and so this is the hypotenuse. I'm going to call it delta x. because that's how far it rolled. And then this is 40 degrees. Okay. And then this is 22 meters. So I know that this 22 meters is opposite the 42 degrees. So that means that delta x times sine of 40 degrees equals 22. All right. So then I can solve for delta x by dividing by sine of 40. And that's going to give me 34.2 meters. Okay, so that is what I'm going to plug in for delta x. So this is 34.2. Okay, 14.8 squared is 220. 2 times 34.2 is 78.4, or 68.4, excuse me. Okay, which I then divide both sides by 68.4. And I get that the acceleration is 3.2 meters per second squared. So, when you are asked if something is rolling and you are asked to determine the acceleration of the object, what you should do is you should use energy to figure out the final speed, and then using that final speed, use kinematics to solve for the acceleration. Okay? All right. The next thing I wanted to talk about is composite objects. So not every object is like a sphere or a disc or a hoop or whatever. Okay, so sometimes you have objects that are more complicated. All right. Now, okay, so the example that we're going to talk about is a yo-yo. And look, there's a front view. So if you're looking at a yo-yo from the front, okay, it's kind of made up out of 3 pieces. It's got 2 discs on the side, and then it's got a little like axle disc in the middle. Okay. If you were looking at a yo-yo from the side view, okay, then you're gonna, let me just make sure that this is, then there's the side of the yo-yo, and then here's the axle in the center. Okay. All right, and let's suppose that the inner disc has a radius r1 and the outer disc has a radius r2. Okay, and so the yo-yo is spinning. Now, a single disc has an inertia of mr squared. Okay, or excuse me, 1/2 mr squared. This is for a solid disk. Okay, so what if we had a excuse me. So what if we have a yo-yo, which is basically made up out of 3 disks, okay? So the total inertia of this yo-yo is going to be the inertia of the left side plus the inertia of the right side plus the inertia of the center part, okay? So all 3 of so it's the inertia is just going to be the sum of the 3 parts that build up the yo-yo, okay? So that's what composite means, right? It means made up out of other things. So any shape, if you want to know the inertia of that shape, and it's made up out of these simple components, you can calculate the inertia by just adding up all of these simple components, okay? Let's assume that the 2 sides of the yo-yo have masses m2. They're identical. Otherwise, the yo-yo as it rolls would be doing weird stuff. And then let's assume that the middle part has a mass m1. Okay? So the inertia of the left part is going to be, the left part has a radius r2 and it has a mass m2. So it's going to be 1/2 m2 r2 squared. The right part is going to have an inertia that is identical because they're both similar, all right? So plus 1/2 m2 r2 squared. So that's the right part. The center has a smaller radius and a different mass. So for the center, we have 1/2 m1 r1 squared. So this would be the inertia of the yo-yo, which is built up out of 3 different parts. I could do some simplification if I wanted to, because these 2 are identical, so they combine to just make 1/2 plus 1/2 is 1. So you just have m2 r2 squared plus 1/2 m1 r1 squared. Okay? So you would do that and you would compute some number. Okay? So you get some number for that. All right? But let's think about, how does a yo-yo roll? All right? And we have to be careful here. So if I wanted to know what is the kinetic energy of a rolling yo-yo, there's a couple different ways it could roll, okay? So let's imagine looking at this from a side view. The yo-yo could be rolling, so here's the yo-yo from the side. It could be rolling along its outer edge, okay? Or if we think about a yo-yo that's actually unwinding, we could have something where the yo-yo is rolling like this, where it's rolling about that inner circle, okay? So if we have this case, because the radius of the outer circle was r2, then we would have v equals omega times r2, because that is the circle that it is rolling about. But if it's rolling about this inner circle, like this, then it would be v equals omega times r1, because this was r1, if you recall. All right, so we have to, if we have a more complicated object, we have to be careful about which circle that it is rolling along, okay? So always, the kinetic energy of the rolling yo-yo is going to be 1/2 mv squared plus 1/2 I omega squared. But in this case, the kinetic energy is going to be 1/2 mv squared plus 1/2 I. And for this one, for omega, I would plug in v over r2 squared, okay, because this is the circle that it's rolling about. And here I would plug in 1/2 mv squared times plus 1/2 I v over r1 squared. Okay? So I guess the point I'm trying to make in this rambling discussion is that if there are multiple circles that the object could potentially be rolling about, you have to be careful about which circle you're talking about, because that's going to affect the rolling relationship. Okay? So that's something to think about. All right, so we're going to do one last topic here for today, which is combinations of rotational and translational motion. So let me give you an example. What if we have a pulley? Okay, so we have a pulley. Here's the pulley. It's attached to the ceiling. Okay, so the pulley has inertia, we'll say 5 kilogram meters squared, and radius 0.1 meters. Okay, and then down here we have a floor, and there's a mass that is right here. This is a 3 kilogram mass. All right, and then on the other side there is a 10 kilogram mass, and those masses are connected to each other by a string that goes over the top of the pulley like that. Okay, this mass right here, the 10 kilogram mass, is we will say 4 meters above the ground. Now obviously the 10 kilogram mass is going to fall, and as it falls, it's going to pull up the 3 kilogram mass. All right. So the question is, how fast is the 10 kilogram mass going just before hitting the ground? Okay, so what's going to happen is the system is going to go to, the system is going to go to something that looks like this. It's going to do that. Okay, so we want to know how fast is that going. So the masses essentially trade places. So as this one is just about to hit the ground, this one is going to be up in the air 4 meters. Okay. And furthermore, because these two masses are connected by a taut string, this one is going to have an upward velocity that is exactly the same. All right? So we're going to use conservation of energy to solve this problem. Initial energy equals final energy. This system is starting at rest. Okay? The pulley, we don't have, okay, so the 3 kilogram mass is on the ground, so it has no gravitational potential energy. The 10 kilogram mass is in the air, so it has gravitational potential energy. And also the pulley has gravitational potential energy, but we're not going to worry about it because the pulley isn't moving up or down. It's staying at the same elevation. Okay? So basically my initial energy is only the gravitational potential energy of the 10 kilogram object. So I'll put that as U10. Okay? Now if we think about the afterwards, the 3 kilogram mass has been lifted up into the air. So now the 3 kilogram mass has gravitational potential energy afterwards. The 3 kilogram mass has kinetic energy because it's being pulled upward. The 10 kilogram mass has kinetic energy, but it no longer has potential energy because now it's at ground level. And so this is almost our energy equation, but we have one more source of kinetic energy, which is the kinetic energy of the pulley, right? Because as these masses move, the pulley starts turning and it gets rotational kinetic energy. All right. Now, an important point is that the pulley, okay, the pulley only has rotational kinetic energy because it is it's staying in the same place. It's spinning in place. Okay. So going to the next line. So I have this is mgy. So I have 10 times gravity, which is 10 times a height of 4 meters. Okay. The gravitational potential energy of the 3 kilogram mass is going to be mgy, 3 times 10 times 4. The kinetic energy of the 3 kilogram object. Now, the 3 kilogram object, it is not rotating. It's translating upward. So this is what I was getting at, is we have the pulley is rotating, but the two masses are translating. So the appropriate energy for these ones are going to be just 1/2 mv squared, just translational kinetic energy. Whereas the pulley is rotating, so its kinetic energy is 1/2 I omega squared. You get what I'm saying? So I hope you do. This is a little bit tricky. So we have plus 1/2 times 3 times v squared. So that's the kinetic energy of the 3 kilogram object. Translational only. Let me write that in. Translational only for both of these. And here, for the pulley, we have rotational only. Okay. So for the 10 kilogram mass, I have plus 1/2 times 10 times v squared. And remember, these two masses are connected by a taut rope, so they have the same speed. All right. And then we have the pulley, which is 1/2 I, the inertia is 5, times omega squared. All right? So I'm going to do a little simplification. So this is 400. This is going to be 120. This 3/2 is 1.5. Half of 10 is 5. Half of 5 is 2.5. All right? Now, here's the thing. This pulley is rotating, and so it's going to obey a relationship just like something that is rolling. So because the pulley is rotating, it's going to obey V equals omega R. Okay? So what that means is that omega is V over R, which is going to be V over, and the radius of the pulley is 0.1. So omega equals 10 V. Okay? So again, because the string is basically causing the pulley to rotate, there's a connection between the rotation of the pulley and how fast these masses are moving. And it's the same relationship as rolling. So if I subtract this 140 over to the other side, I have 260 on the left-hand side. If I combine these two, 1.5 plus 5, I get 6.5 V squared. And then I have plus 2.5, and then omega is 10V. So I have 10V quantity squared. So 10 squared is 100. 100 times 2.5 is 250. So I have 260 equals 6.5 V squared plus 250 V squared. 260 equals 256.5 V squared. And I can solve that for V squared. It's going to be about 1. Really close to 1 meter per second. Okay? So I kind of showed all the steps in gory detail because it's really easy to have a math mix-up in this type of a problem. Okay?